Ladies and gentlemen, let's consider 4 additional trigonometric functions, shall we? And in order to do so, let's look at our picture of a circle with center at the origin and a radius r and an angle alpha in standard position. And what I'd like to do is to define a function called tangent, in which we then will take that angle alpha and map it into a number. And the number that I would like to pick, looking at our picture here, is going to be the ratio of v sub 1 divided by u sub 1. Okay? So that alpha then is mapped into v sub 1 divided by u sub 1, where of course u sub 1 cannot be equal to what? Cannot be equal to 0. Another function that I'd like to define, called cotangent, is going to be that angle, or that function, in which we'll take an angle alpha and map it into another number. And the number that I like to pick, looking at our picture, is going to be u sub 1 divided by v sub 1. All right? And u sub 1 divided by v sub 1, where of course in this case v sub 1 cannot be equal to 0. A third function that I'd like to define is called secant. And I will define that as an angle alpha mapped into, and the number that I would like to pick is going to be r divided by u sub 1. All right? With r divided by u sub 1, where u sub 1 of course is not 0. And finally, a fourth function I'd like to define is called cosecant, in which we'll take an angle alpha and map it into a number. And what do you think that you would like to make this definition, Bill?
R over v sub 1.
R divided by v sub 1, where v sub 1 is not 0. Now again, these are simply definitions in which we have an angle alpha, and we will then map it into a number. Let's look at this from another point of view. In fact, what we might think of as our circular functions. We can define them in exactly the same way, but now let's change our notation a little bit and talk about the set of all ordered pairs of the pattern x comma, and our second element of the ordered pair is going to be, in this case, the name of the function. Let's call it tangent of x. Notice the abbreviation of tan x, such that tan x then is going to be equal to, and let's use the same definition, which is going to be what? What do we like to say here, Doug?
V sub 1.
V sub 1 divided by u sub 1, where again u sub 1 is not equal to 0. Now here then is a set of ordered pairs such that our function is defined in this fashion right here. Again, our set of ordered pairs, x comma cotangent of x, is such that the cotangent of x you then would like to say is equal to, and who is it, Steve?
U sub 1 divided by v sub 1.
V sub 1, where v sub 1
It's not equal to 0.
is not 0. The secant function is a set of all ordered pairs of the pattern x comma secant of x, such that the secant of x is going to be equal to, and Tim?
R divided by v.
All right, now in the cases we have it here, our circular functions, remember we're on the unit circle in which the number r is indeed equal to 1. So Tim?
1 divided by u sub 1.
1 divided by u sub 1 then is our definition of the secant function, where u sub 1 is not 0. And finally, the cosecant function may be defined as what? What can we say here? Someone, Dick?
1 divided by v sub 1.
All right, the cosecant. Notice our abbreviation here is CSC. The cosecant of x is equal to 1 divided by what? V sub 1, where again v sub 1 is not equal to 0. All right, now again our circular functions defined on the unit circle and our trigonometric functions in terms of a number of an angle alpha are the same. All right, in which here we now are thinking of a real number x, which is the arc length on the unit circle. Well, let's look at these functions again, and perhaps from a slightly different point of view. And now looking at our picture in which we have the tangent of x, if we then were to consider the tangent of x, we've defined it as v sub 1 divided by u sub 1. The cotangent of x we have defined as u sub 1 divided by v sub 1. And what then do you think is the relationship that exists between these two? But we may say that the tangent of x is equal to what? And Dick?
1 over the cotangent.
1 over the cotangent of x. Similarly, the cotangent of x you would like to say is equal to, Doug?
1 over the tangent of x.
1 over the tangent of x. Looking at the secant function, our definition of secant was what? 1 over u sub 1. But if you recall, our definition of cosine was what? u sub 1 over 1, so to speak. So therefore, another name for the secant of x is going to be equal to, Bill?
1 over the cosine of x.
1 over the cosine of x. Similarly, the cosecant of x you would like to say is equal to, Dick?
1 over the cosine.
1 over the sine of x. In fact, I may also say something about the sine of x. The sine of x is then going to be equal to, Brenda?
1 over the cosecant of x.
1 over the cosecant of x, and of course the cosine of x is equal to, Brenda?
1 over the secant.
1 over the secant of x. And notice the relationship that exists here in that these functions are reciprocals of one another. The tangent and the cotangent are reciprocals, the secant and the cosecant are reciprocals, and the cosine are reciprocals, and the cosecant and the sine function are reciprocals. As a matter of fact, let's look at the tangent function again for a minute. Even though it doesn't come into these reciprocal relationships, I think it's worth pointing out. The tangent of x, we've said, is what? Looking at our picture, it's what? Our definition is v sub 1 over u sub 1. But give me another name for v sub 1 in terms of our definitions. Another name for v sub 1 is sine of x, and another name for u sub 1 is cosine of x. Therefore, another name for the tangent of x is equal to what? Sine of x divided by cosine of x. Similarly, another name for the cotangent of x is going to be equal to what? Cosine of x divided by the sine of x. And these two relationships also turn out to be quite significant as we continue our work in trigonometry. Well, let's now look at some of the graphs of these functions, shall we? And before we look at the graph, let's again look at this picture of a unit circle, and let's think about, for example, the tangent function. Now, if the number x, say, were equal to 0, all right, the tangent is v sub 1 divided by u sub 1. In that case, the height v sub 1 is what number? It would be equal to 0. Therefore, what then would be the tangent of 0? 0. As x continues on around here, for example, right at pi over 4, say this length as I have it here in this picture, v sub 1 and u sub 1 are the same numbers. Is that right? The same number. Therefore, what then is the value of the tangent of pi over 4? It's equal to 1. And therefore, the tangent function is going to go from 0 to 1 as x goes from 0 to pi over 4. Is that right? As x continues, let's say some number up here such that this is the height, v sub 1, but u sub 1 is quite small. So therefore, what is the value of the tangent? It is getting, certainly it's getting larger. And finally, right here at pi over 2, what can we say about u sub 1? It's equal to 0. Therefore, what can you say about the tangent of pi over 2? It's undefined. All right? Now, if we were to continue in a negative direction, suppose x, say, were a negative number, v sub 1 would be negative, and u sub 1 would still be positive. Therefore, what can you say about the tangent value? It's what? It's negative. And in fact, if the value of x, say, were right here at a negative pi over 4, what then is the value of the tangent of negative pi over 4? Negative 1. And say a number down in here might be negative 10. And a number as we approach negative pi over 2, what then is the value of the tangent approaching? It's approaching infinity, or in fact it is undefined. Well, let's think about that and try to make its graph. As a matter of fact, I've already made the graph of these functions, and here we see the graph of the tangent function. And again, notice right at 0, the tangent of 0 is 0. When x is, say, at pi over 4, which is between 0 and pi over 2, the tangent is at 1, and that's, say, this point. And as x approaches pi over 2 from the left, the tangent approaches positive infinity, and right at pi over 2, it's undefined. Similarly, on the negative side, it comes on down here to a negative infinity. Now notice, as soon as we go beyond pi over 2, the value of the tangent then comes down here and approaches a negative infinity, and then it comes on up, and right at pi, the tangent of pi is 0, and goes on up to a positive infinity between pi over 2 and 3 pi over 2. Well, we have certainly a function here. What can we say about the domain of this function? And what values can we take on here for the x values? And what can you say? All real numbers. X belongs to the set of real numbers, and there are some values which must be excluded. Is that right? Every place where the value approaches where the tangent is undefined certainly cannot be in our domain. So what then can we say? And x is not equal to, well, certainly it's not equal to this point, this number, which is what? Pi over 2. And in fact, let's generalize this. X is not equal to pi over 2 plus and some multiple thereof. And from here over to here is what number?
Pi.
Is pi. From here, say, to here is what number?
Pi.
Is pi, a negative pi in this case, a negative 2 pi, a positive 5 pi. So x cannot be pi over 2 plus, Doug,
K pi where K is an integer.
k times pi, where k is an integer. Very good. What then can we say about the range? And the range are all the values that y can take on, and it must be what set of numbers? Charles?
Real.
Y then belongs to the set of real numbers. Again, we have a function which is periodic, and what do you think you can say about the period of this function? Say from this point to this point is one period, and then it repeats itself, and so what then is that length, Brenda?
Pi.
It then is of length pi. All right? Now, this is the graph of the tangent function, and I think looking at it, we can easily arrive at the graph of its inverse, namely the cotangent function. Now, right here, for example, when x is 0, the tangent of 0 is 0. And what then is the reciprocal of that number? Well, it is what? It is undefined. When, say, x is at pi over 4, the tangent of pi over 4 is at 1, therefore what's the reciprocal of 1? 1. So that number should be on its graph. Is that right? So it looks like our graph is going to have to come from up here, come on down, pass through this point, and right at pi over 2, what do you think the cotangent of pi over 2 is going to be? It's going to be 0. Is that right? And then, in fact, you suspect that it's going to continue on down this way, and as we approach 0, the cotangent function is going to approach what number? Or it's going to approach what? Negative infinity. Is that right? Well, thinking about that and looking at the graph of the cotangent, I've actually made this graph, and here it is. And what then can we say about the domain of x for this function? Its domain is going to be what? X belongs to a set of real numbers, but there are some values which must be excluded. Now, where are those points which cannot be on the graph? Well, certainly when x is this point, namely 0, and also this point, which is at pi, and say at negative pi. So therefore, what is your conclusion, Phil?
X does not equal pi k where k is an integer.
And x is not equal to pi times k, where k is an integer. Very good. What then can you say about the range of this function? And it's going to be, Tim,
Real numbers.
over the set of real numbers. Y then belongs to the set of real numbers. And what about the period of our cotangent function? It's going to be, Dick,
Pi.
it's going to be of length pi. Very good. Well, let's now turn to the graph of the secant function, shall we? Now, notice in this graph, what I have first drawn is a graph of the cosine curve as a dotted line. And remember now that the relationship between the cosine and the secant curve functions are that they are inverses of each other. So from the cosine curve, let's think about the inverse of each one of these heights, and then we can arrive at the graph of the secant. Is that right? Okay. So for example, when x is 0, we know that the cosine of 0 is at 1. Therefore, what's the reciprocal of 1? 1. Therefore, this point must be on the graph of the secant function. When x is, say, at some number here, this height is going to be the value of the cosine. Therefore, the reciprocal of that number, which is less than 1, must be what? Its reciprocal must be greater than 1, and that's going to be this height here. As x approaches pi over 2, the cosine approaches 0. Therefore, its reciprocal must approach what? In positive infinity. Similarly, on the negative side, that is between 0 and negative pi over 2, the cosine function is approaching 0. All right? Therefore, its reciprocal must approach positive infinity. Now, as soon as we go into, say, the second quadrant, that is from values of pi over 2 to 3 pi over 2, notice that our cosine function is below the x-axis. Therefore, its reciprocal value is going to be 1, which is going to give us a graph similar to this. Everyone agree with that? Okay. Now, what then can we say about the domain of the secant function? We are interested in all values of x, which are over the set of real numbers, except there are some which we must exclude. in that x cannot be equal to what numbers? Well, a typical one that we must exclude is this point, say at pi over 2, and another one that we must exclude is at 3 pi over 2, another one is at negative pi over 2, so what's your generalization? But,
Pi over 2 plus k
Malcolm? Pi over 2
plus k pi.
plus k times pi, where k then is an integer. Now what about the range of this function? Notice that our graph is such that we must be outside of some interval as we see it here. So what then can you say about its range? Peter?
Y is greater than the absolute value of 1.
All right, now not quite the y is greater than the absolute value of 1, but it's the right idea. Very good. What else can we say, Brenda?
The absolute value of y is greater than 1.
The absolute value of y is greater than or equal to 1. I think that's really what you had in mind, Peter. Very good. And now what can we say about the period of the secant function? And remember now, say going from this point over to this point would then be one period. Is that right? Or else we may start, say, at negative 3 pi over 2 and come on up here to pi over 2. And what then is the length of that period, Doug?
2 pi.
It's then going to be of length 2 pi. But what then is the length of the cosine function? What is its period? It is 2 pi. So you suspect that its reciprocal is also going to have the same period. Well, let's then look at the last graph, namely that of the cosecant function. Again, I have made a dotted line, which is the sine function, the graph of the sine curve. All right, now what then can we say about its reciprocals? Well, I think you will agree that its graph is going to look like this. And what then can we say about the domain of this function? X then is going to belong to what?
Real
The
numbers.
set of real numbers, and x is not equal to some numbers. Well, what values can x not be? It cannot be 0 and all multiples of pi thereof. Is that right? So how then may we say that? But, Doug?
K pi or k is an integer.
K times pi, where k then is an integer. Very good. Also, what can we say about the range of this function? Again, you were outside of this interval. And Rick, what can we say about that range?
The absolute value of y
The absolute value of y
is greater than or equal to 1.
is greater than or equal to 1. Very good. And also, what can we say about the period of this function? And we can see that it is going to be
2 pi.
also 2 pi. Of course, the period of the sine function we know is 2 pi, and so its reciprocal, you suspect, is going to have the same period. Very good. Now, let's look at one last idea in this lesson, and that is the SIGNS's, the signs of these various functions. Now, if we think in terms of our coordinate system, our first quadrant is here, such that, now just imagine, say, a unit circle on this graph as I have it here, on this coordinate system. Now, the sine value, think geometrically. The sine of x has to be the height, and the cosine of x has to be that length. Is that right? And in the first quadrant, the sine of x is going to have to be what kind of number? Is it positive or negative?
Positive.
It's positive. Certainly, it's greater than 0. If the sine of x is greater than 0, its reciprocal must also be greater than 0. So that automatically gives you its reciprocal function. What about the cosine number? It must be this length. It is greater than 0. Its secant value is greater than 0. The tangent is that positive number divided by this positive number, so therefore it must be greater than 0, and the cotangent must be greater than 0. Notice in the first quadrant, everything is positive. Let's look at the second quadrant. The sine, again, is the value above the x-axis, so what can you say about the sine of x? It's positive. Therefore, its reciprocal is positive. The cosine is the value along the x-axis in this direction. It must be what number? Less than 0. Therefore, its reciprocal is less than 0. The tangent is that positive number divided by this negative number. Therefore, it must be less than 0. The cotangent is less than 0. In the third quadrant, the sine now is this negative number. Therefore, the sine of x must be less than 0. The cosecant less than 0. The cosine is this negative number, therefore it must be less than 0. Its reciprocal is less than 0. The tangent is this negative number divided by that negative number, therefore it must be greater than 0. And therefore its reciprocal is greater than 0. Finally, in the fourth quadrant, the sine is still negative, therefore the cosecant is negative. The cosine is positive. The secant then must be positive, and therefore the tangent must be negative, and the cotangent must be negative, and that then will establish your sines. Think geometrically, and I think everything will take care of itself. Let me give you your homework assignment for next time.